Right, so how many dimensions are there? So this is a subject a lot discussed, and the reason why I've done this is because I somehow got involved in a discussion group recently in which people were making a lot of comments about this, but nearly all to absolutely no purpose whatsoever, so I thought let's have a bit of clarity. Hang on, what's that done? It's not moved my thing on. Oh, it's that one. That's the one. Right, so what are dimensions all about? Well, they're certainly all about orthogonality, and they're all about Pythagorean addition. In other words, squares of numbers. And squaring seems to have a special relevance. We have the Lou just telling us about the quadratic Hamiltonian, and it seems that the quadratic is very important in physics, more than anything else. So it's got a special relevance. So we measure, our measurements are all based on counting numbers, integers. Can't really imagine counting without having any integers. Now, we know that every sum of integers gives an integer, so we can have a complete progression and set up our measuring system that way. There's an infinite sequence of integer sums, the integers expressed as integer sums, and this is the basis of all observation. There's no meaning to observation unless you can actually count. However, if we look at numbers, there is another alternative to simply counting numbers, and that's to use Pythagorean triplets. And there's an infinite sequence of these. There's an infinite sequence of sums of squares of integers that are themselves squares of integers. And we can always find, to any squared integer, we can always find another squared integer that will give another squared integer when we add them together. And this is what number factorization is about. For example, that's how we would do it down there. Just difference of two squares, and if a minus b is a factor of c, then we can set up such a number. And we can therefore always create an infinite sequence of Pythagorean connections with larger and larger numbers. So it's another way of expressing the factorizability of integers. But this is impossible for any exponent greater than 2, as we know. There's not even a single instance of it in the whole of arithmetic. You can't add up any cubes or any fourth powers or anything of that kind. It simply cannot be done. And so it seems that squaring and Pythagorean in addition are actually fundamental to arithmetical operations. And in some sense, a uniquely valid alternative way of constructing an infinite sequence of divisions in an infinite measuring scale. So it's an alternative to just using integers is to use squared integers. It's a counting ladder similar to regular numbers, but with its own rules and in the same way as regular numbers define their own rules. So I think this is really the ultimate meaning of dimensionality. This is why we have it. This is why it's squared, and this is why squares are important in physics. So if we can set up such a system, then the things that separate these two infinite series will become significant. Integers and squares of integers. And the fact that they are separate and they're not the same method of counting means that we can set up the condition of orthogonality. Because in orthogonality, the squared numbers don't add up in the same way as the regular ones. Sometimes squared numbers are possible and regular ones aren't. And that's what we mean by orthogonality. So this is, we think, is the condition that creates dimensions. Now, of course, the intuitive idea that there are 3 dimensions of space is ancient, possibly millennia in origin. And same as Pythagoras' theorem, that's certainly very old indeed. And the first idea of orthogonality, though, comes a bit later, I think. It doesn't actually come from dimensions in the same way. The idea that things are orthogonal and not just... I mean, Pythagoras' theorem is orthogonality, but I don't think you realise immediately that that's what it is. To understand the orthogonality of real numbers, we have really to look at a different kind of number. We've got to look at imaginary numbers, ones that are squares of that lead to negative squared numbers. Now, imaginary numbers are incommensurate with real ones, though the squared ones are not, and that is classic example of orthogonality. And so it immediately forces into defining an orthogonality. Truly orthogonal dimensions are incommensurate as to addition, but commensurate to squared addition. And this is exactly what we get with imaginary numbers. So we can actually use the fact that they're very similar to two dimensions in the Pythagorean sense, so we can use Pythagorean two dimensions to represent them. So this is what we use in the Argand diagram with horizontal real, vertical imaginary. But we don't get Pythagorean addition out of it. What we have to do is use a special multiplication combining the real and imaginary numbers using the complex conjugate. So we can't do it by direct Pythagorean addition. But it is a kind of analogy to it. So if we like, the real and imaginary numbers are a kind of two-dimensional representation, but it's not a standard one. It's not the same as the two-dimensional aspect of three-dimensionality in space. And this distinction is a very important one in physics, and it will continue to be so. Now, if we look at dimensionality of space, this is our intuitive understanding. It tells us that these dimensions are distinct and orthogonal. We have three distinct and orthogonal dimensions, but each have identical properties. There's nothing different about them, which is quite different from adding real and imaginary numbers, which are also distinct from each other. And this is the real imaginary is a kind of broken symmetry, whereas the ordinary three-dimensionality of space is not a broken symmetry; it's a real symmetry. So but interestingly, it's the broken symmetry which gave us the first clue into the meaning of the real perfect symmetry. And this is the discovery of quaternions in 1843 by Hamilton. Hamilton realised that he discovered the meaning of three-dimensionality. He was the first to actually get any clue into it, and it's still the only clue we have into it. It's still the only way in which we can understand that three-dimensionality is really special in some way. And what he was trying to do was extend the complex numbers into the third dimension. He had the Argand diagram in front of him, and he wanted to extend it into three dimensions. So he proposed to draw a third look at that diagram. That's what he tried to do on the left. He tried to find a system in which there was real numbers and two imaginary numbers, but the two imaginary numbers multiplied together didn't give anything that made any sense within the system. So eventually, after a lot of trouble, he created a system of three imaginary numbers which was cyclic. But to do so, he had to do something that violated a cardinal principle of algebra as then known, which is the principle of commutativity, the fact that AB and BA were the same thing. AB in this system had to be minus BA, and this was a breaking the rules of algebra as then known. He removed the real axis, had three imaginary axes, with units all different from each other, but all equating to root minus 1, and following a rotation cycle, giving us those rules ij equals k, ki equals j, jk equals I. So he now had a closed algebra with four basic units, which he called quaternions. But one is the fourth unit, and double the size of complex algebra, and four times the size of real algebra. And the question was, can we do that again? Can we say, push it to another dimension, say, let's make L another version of ijk, and in fact you can't. And this theorem was proved by Frobenius in 1878, that you can't do that. And if you try it, if you're just trying it out with a pen and paper, you can quickly find out you can't do it. But the proof is quite difficult. Now, the threeness isn't the primary cause of the three-dimensionality of space. It's really anti-commutativity that does it. So that's the key thing. It's not three dimensions, it's anti-commutative dimensions that are really important. If we have two axes anti-commutative with each other, then we can't draw any other axis that's anti-commutative with them, unless it's ij. So we can't make up another one. If we wanted to, we can't do it. We also call ij as k. So it's anti-commutativity that forces the three-dimensionality, and this explains the strange arbitrariness of dimension 3. Now, if we had commutative things, that AB equals BA and so forth, then we could extend to ijk, lm without limit. We could have an infinite number of dimensions that were commutative. And I like to think of it as anti-commutative things know about each other's existence, but commutative things don't. So I always knows that it's a partner of J and K, but it doesn't know about anything else. And anything that's commutative simply doesn't know that anything else exists.
I'm a little confused about what you mean by the anti-commutative things know about each other. I think you're assuming something else, because we can do Gaussian algebra, for example, where
That's not a division algebra, though.
And the anti-commutative.
Oh yeah, but that's not a division algebra.
Many other directions.
I'm basing algebra on numbers, division algebra. I'm not basing it on anything else. You can actually make up other rules, yeah. You can create other algebras based on other rules, but this is an extension of numbers. This is division algebra. That's what I'm arguing for.
What assumption are you making?
What's it?
What assumption are you making that you have to have another direction that we call K for ij, and then it closes? You're assuming that the algebra closes.
Yeah, you're assuming division algebra.
Closes at 3.
But you're assuming that you get divided.
Arbitrarily, 3 came out because you assumed it closes.
Yeah, that's correct. No, you didn't.
So you didn't derive 3.
I didn't derive 3. Someone else did. This isn't my mathematics. This is standard. I'm simply quoting the official standard line on it.
I mean, it seems to me that what forced 3 was something else. Namely, you wanted a division algebra, and you got one.
Yeah.
And you wanted it to be associative, and you got one.
Yeah, well, we're coming to that.
With all that, you were forced into 3 plus 6.
Exactly, that's what I'm saying. That's what I'm saying. Exactly what I'm saying. You've got two conditions. You've got division algebra and associativity. Well, I haven't mentioned anti-associative yet. So it works well, but it requires a reversal of sign when you reverse the order of multiplication. It's trivial to show that, because for example, we take the product ij, ji, multiply the j's out, you get minus 1. You're left with minus ii. You can easily show that 1. So therefore, ij and ji can't be the same. There's just one exception, and this is what I was going to bring up, is that if you break another rule, associativity, which is AB times C is the same as A times B times C, then you can actually create an algebra with 7 imaginary components, which we call octonions. Now the trick can't be repeated again. If you want a division algebra, if you want it to be a number algebra, division algebra, then you've got to have one of these 4. These are the only 4, and those are the norm means the unit is squares to 1. Norm means the unit is squares to minus 1. And also, these 3 higher algebras are not totally compatible. The 8 dimensions of octonions don't completely contain the 4 of quaternions as a subset, nor the 2 of complex algebra. It's not as simple as that you can just extend the algebra, that they have differences. No, and the kind of dimensional found in space is that of a non-conserved quantity. This is very important. This is a very important aspect when people are talking about extending the dimensions of space. They often ignore this. Space is a non-conserved quantity. It's got affine structure and rotation symmetry. Affine structure means that you can endlessly recreate the dimensions as long as you get the same result from them. There's no fixed set of 3 dimensions. You have to have 3 dimensions, but you can do it any number of ways you want, endlessly. And you can't actually stop space doing that. It's not that you can make the choices. Space can make any choices it wants. And also there's rotation symmetry between the dimensions. You can exchange one for another. You can't just pick anything you want. So this kind of dimensionality found in space, characteristic of a non-conserved quantity, can only exist for 3 dimensions unless the system is anti-commutative. And even then it's only for 7 dimensions. So you just can't push space out to be whatever you want. You can't say, I want 10 dimensions of space, or space and time. You can't do it. It's not mathematically possible. You cannot extend space as we know it to 9 dimensions. What you could do is embed the 3 dimensions of space in a higher dimensionality, but they can't be extended to become one thing. It would then be a more complicated structure. And that's just mathematical.
Is this an absolute
yes, absolutely.
Of string theory then?
No. We'll come to string theory. It is a refutation of what many people think of as string theory and push the idea that you can just have as many spatial dimensions. You can't. It's just nonsense. But if we want space as we know it to be part of something bigger, then you can't just make it 9 of the same.
So when you speak of extending space, you mean and carrying the algebra structure.
Yeah, exactly.
That for you, when you speak of space, it has to have that algebra structure.
Yeah, to me it has to, because it's not space otherwise. It's not space as we know it. I'm saying we can't extend space as we know it and add another 6 dimensions. It cannot be done. There is no way of doing it. What you can do is you can embed it into something that's got 6 other dimensions of some other kind, but you can't just say, let's make space 9-dimensional. It's complete nonsense.
You can't say the other dimensions are rolled up either.
That's right. You can't. You're absolutely right there. What I'm saying is you can't do that because all the dimensions have got to be the same if it's like space. And they've also got to be rotation symmetric, and they've got to be affine.
They got to have a metric between three space and that, right?
So you can't just say, let's have space and roll up some of the dimensions. That's complete nonsense.
But doesn't this depend a lot on the definition of dimension? I mean,
that's what I'm saying. I'm saying you can't have it as we know it. You have to have a new definition of dimension if you want to do that.
Well, by as we know it, you mean as all the rules of algebra
yes.
specify.
As space as we have it now, we cannot multiply by 3. You know, and it would be the same. We would preserve that bit of space the same. It wouldn't be. But we can do other things. I'm not denying we can do other things, but we can't do that.
If I assume that 3 dimensions is a property of the display system that we are biologically endowed with, I can certainly imagine us evolving into some systems that allow us to visualize 4 dimensions of 5 dimensions.
We can't. It's not algebraically possible. However, we can do other dimensional tricks, and I'll show. We'll do that. Well, they are tricks. Well, they might be useful tricks, but we can't actually just say let's push it out to 9.
So I guess I have to reject on the grounds of classical topology, in as much as the standard usage of space has been abstracted from any algebra that might be associated with it.
Yeah, sure. I mean, you can do topologies and geometries and things, but you can't actually do a division algebra extension. And the division algebra is important for us for measurement and observation. And that's what I'm saying.
You can't swing your ruler into the extension.
Yeah.
The ruler stays in 3.
I'm saying the application of vision algebras to space is crucial for physical purposes where measurement and counting are fundamental processes. So if we're talking about measurement, counting and things like that, we can't do it. But certainly you can draw 4-dimensional, 5-dimensional spaces and so on. But that is not what is our spaces. Anyway, so the kind of dimensionality found in space characterizes a non-conserved quantity with an affine structure and rotation symmetry dimensions can only exist for 3 dimensions unless the system is also anti-commutative, and even then it can't exist for more. That's what I'm saying there. So its dimensions can't be fixed. They're endlessly reconstructible in respect of our attempts to fix them. And we can't privilege some dimensions with respect to others if we want our space to be extended. We can't just say, oh, those dimensions are different. We can't do that because it's a non-conserved quantity. All the dimensions have to be equivalent. We can't make some more equal than others, as it were. So the dimension does have the freedom to transform into each other without separating out some particular dimensions to which it doesn't apply. We can't do it. Now, let's recall the different ways that we've represented 2 and 3 dimensions. This is a profound difference in the most fundamental symmetries of the art of nature. 2-dimensionality reflects duality. 3 reflects anti-commutativity. And the tension between these 2 symmetries, which to some extent I consider as like conservation and creation, it goes a long way towards explaining large parts of physics, biology, the rest of it. It's because these are not the same. The 2-dimensionality is not a bit of 3-dimensionality, not truly, because that 2-dimensionality isn't 2-dimensionality. The 2-dimensional complex numbers can't be extended to 3D, while the 3D representative quaternions doesn't truly incorporate a 2D. You can't separate out 2D and say let's just keep that part as a separate. That's what Hamilton tried to do and failed. Lines, areas, and all that in space couldn't be represented without an underlying 3D structure. They're not 1D or 2D. They're 3D representations of 1D and 2D, which is quite different. And so also 3D and anti-commutative also incorporate something special into nature, the idea of discreteness. They actually create this closure, and the closure creates discreteness. And in nature, it seems to me that all discreteness comes from anti-commutativity. And I will actually say something here. All discrete things are 3-dimensional in some respect. Now, if dimensions are defined through anti-commutativity, then the number of dimensions will always be restricted to 4 if we ignore anti-associativity. If we suppose that the commutative then could go on to infinity, well, we could just simply put spaces where we park various things and consider them orthogonal. Things like the Hilbert space, for example, is of that nature.
So Peter, you said 3 anti-commutativity implies 3 dimensions. Now,
Yeah.
Where does the 4th one come from?
So that's when I say 4, that's the 4th part of the quaternion, the real part. In fact,
okay.
what I'm going to say, it's a double connection. It's anti-commutativity and duality to make it. You can't do it without both. So I'm going to say you can argue that 3 dimensions are part of the larger 4-dimensionality, as the quaternion name would suggest. But you can't even think of the 3 imaginary units without having a real one. Even though you can't draw the real one on the diagram. Well, this one is different from the other 3. You can't absorb it into those axes. The 3 axes of the IJK are interchangeable, but the 1 isn't interchangeable with them. So the relationship is again a broken one, like the real and imaginary complex numbers, which is what it is. It's a duality relationship. Now, if we go back now to quaternions, this is historical importance. They're norm 1, and that put people off using them at the end of the 19th century. And so we're still a step away from explaining spatial dimensions. We've got dimensions or spatial dimensions. Well, Hamilton actually did develop this idea. He developed the quaternion idea. Since they're distinct from ordinary complex numbers, we can actually add complexity to it and create new sets. So if we add a complexification to IJK and 1, I will appear as a unit, and also these will appear as units. So we will in fact complexify the whole thing. And I've mentioned this before in one of my earlier talks. These create what we now call multivariate vectors. So these are the rules for that algebra, and this is writing them in this form, the bold symbols for these multivariate vectors.
Now you'll notice that you now have an 8-dimensional space.
Yes, indeed.
With associativity, but not division.
Yeah, it's not a division algebra. What this is now is a broken symmetry. It's not a true 8-dimensional. It's a broken symmetry. So the objects, as mentioned before, had all the properties required of vectors, except that they had the extra property which eventually merged as spin. And in fact, nowadays, I'll leave that out of power matrices. they have real vectors are these quantities. They're not actually just as we used to use them in standard textbooks. They are actually these quantities. So we know that in addition to the vector scalar, the full algebra requires pseudo-vector quality areas. So it's fundamentally this way, but in another sense, say dimensional as we discussed earlier, in effectively including the quaternion algebra and requiring a total of 8 orthogonal units. So the algebra of those, I don't think I've written it, but the complexified vectors, these things, those, is in fact a quaternion algebra. But now we've gone down a route which makes the whole idea of dimensionality much more problematic. We've effectively combined two different dimensional systems which individually are compatible. We've got the quaternions with their anti-commutativity, and we've got the complex numbers with their duality, and we put those together and they're not totally compatible. We've created the first Clifford algebra, and now Clifford algebra is the way we can in fact imagine a quantity can be embedded into a higher dimensionality without being extended into one. Effectively, Clifford algebra is an endless number of quaternion systems, each anti-commutative to each other, with a complexity added or not, as you choose. But by going down this route, we've crossed the Rubicon. The dimensionality is now much more problematic. We've redefined it in a more problematic way. They're no longer simple, but also compounded, and simple answers to questions yield multiple interpretations. Even space itself gives us a problem. We've explained space is dimensions. We got it as unit 1, but we've got a problem with it. This is a classic example of the Minkowski four-dimensional space-time. And this is what is called a four-vector. This is a vector and a pseudo-scalar unit representing time. And we can imagine creating it by multiplying the quaternion units by the pseudo-scalar unit. So it has 4 dimensions, if you like. And it's widely claimed to be a breakthrough concept. And of course it is a very important concept, a very useful one. However, there are problems with it. It's not obvious why there are only 4 dimensions, because the algebra isn't possible without also having the scalar. We define the algebra to be the vector plus the pseudo-scalar, but it doesn't make sense algebraically without the scalar. So really, shouldn't we have 5 dimensions? And it's not obvious why we couldn't have started from the quaternions and added the pseudo-scalar. Why we had to start with the vectors. Obviously to explain the space we need, but we needn't have started from them. So there are 2 possible ways of defining it. And it also, is it really 4, is it really 5? And the pseudo-scalar used in the combination is time, whereas space has its own pseudo-scalar, which is volume. It doesn't need another pseudo-scalar. So we've added a pseudo-scalar externally to it. So it's not just a mathematical issue, because there are real problems with four-dimensional space-time. It's a very useful concept, as long as we realise we've got problems with it. Minkowski is famous quote, henceforth space by itself, time by itself, doomed to fade away into mist shadows, and only kind of union of the two will preserve independent reality. Well, I don't accept that that's true at all. The mathematical union doesn't disguise the fact there are major physical differences. It's a good mathematical union, but it's a mathematical union, not a truly physical one. Wave-particle duality, essentially, we either go down the space route or the time route. Whichever we do, we choose one or the other, because we've said that there's a physical union as well as a mathematical union, which there isn't. General relativity becomes incompatible with quantum mechanics because it treats time as just another dimension of space, but quantum mechanics requires special differences. Time in quantum mechanics isn't an observable, but suddenly we've got a problem, because general relativity wants it to be incorporated into space as a real 4th dimension. Penrose's twistors is another one, 4 real units, 4 imaginary. Really sounds a very good idea, but he assumes a real 4-dimensionality, and it means he can't generate particle structures. Again, relativistic quantum mechanics doesn't actually use 4 vectors at all, as I'll show later. It uses something a bit more subtle. It uses 4 vectors embedded into something else. So it doesn't carry over as simply as people think. You you need a higher Clifford algebra to be able to do it in the Dirac equation. So I've already said what Clifford algebra was. Once we've established the combinations of these sets, then any level of dimensionality becomes mathematically possible and related to physics. But the concept of dimensionality then becomes ambiguous because the dimensionalities are not necessarily unique. You see, Clifford algebra is only possible, community makes it possible, so we've got several sets of dimensions which we put together, and we can do that. The multiple sets will be defined by the uniqueness of the partnerships within them, but not external to them. Now, the result is an extension of the concept of dimensionality at the same time as denying its uniqueness. This is a typical Clifford algebra. G is also geometrical algebra, is another name for it. M or N. M is the number of units with +1. N is the number of units with -1 norm. And for example, let's say we take this one, 3, 2. This is an algebra with 5 dimensions. But any norm 1 object could be made up from 2 objects with norm -1. You could easily do it. So the algebra might be reconstructed as 2, 4. Right? We take 1 off that and add 2 onto that. So this is now 6 dimensions. And it's exactly the same algebra. It does the same job. But it's ambiguous. So Clifford algebra allows us to do this, but it doesn't allow us to extend our 3D space into more dimensions. I've already gone through that. So if there's a deeper level of being in dimensionality, it can't come from space alone, because we can't extend our space into these dimensions. It must come from something else. And I'm saying it's coming from those parameters which exist at the same fundamental level as space and time. And I've worked on this for a very long time, and to my understanding, there are only 2 other parameters of that order. One is mass or mass energy, and the other one is charge, which is the source of the strong and weak electric interactions. And this is the Klein 4 group that I found long ago served the purpose of uniting these things in a symmetry, rather than an individual unification, but a symmetry. This is the diagram that my colleague Vanessa Hill did at my request, showing the interrelationships between these various things. And after 30, 40 years testing, I've never found any exception to this symmetry. I've always found it true. So these exhibit paired dualities with each other. And these dualities can be expressed in an algebraic way. That's the interesting thing. 2 of the dualities are real and imaginary. We go back to that. Real and imaginary. Real numbers, imaginary numbers, whatever. Norm 1 and norm -1. A second one is commutative and non-commutative, anti-commutative in fact, and that's obvious as well. And the third one, conserved and non-conserved, is almost certainly in this category. And I think it's the ones that have the extra pseudo-scalar that are the non-conserved ones. So if we do that, we can construct these parameters to have these algebras, and these are the sub-algebras related to the parameters. So you've got scalar, complex, quaternions, and multivariate vectors. And my understanding is that there isn't any other information in physics other than what can be got from that. So this is where the source of dimensionality of any extra kind has to come. So charge now becomes identical as the place where the quaternion algebra is already present in nature. Is directly present. Well, we had quaternions before we knew what to do with them, just like we had the laser before we knew what to do with it. But we couldn't manage without it now. I think the same is true with quaternions. But I think they find their home in the representation of charge and mass. It has its own scalar part, but it can be combined with mass as the scalar. Again, it's got its own scalar. Its scalar is its scalar values of the charges, but it can be combined with mass in a new 4-dimensional algebra, which in the same way as we combined time and space. So we got a mass charge similar to space-time. But it's not so simple as we might think at first. It's yet another problem, because a more complicated structure again is required. Yes, there is also also a difference in that these quantities are conserved. They don't have that rotation symmetry and affine structure that the other, the non-conserved ones have. So we can actually write it all down in the language of Clifford algebra that way. So this is the Clifford algebra language, but this is the alternative languages from which they could have been derived. Now we can also set it out like that, and we can. There's the thing I was mentioning a couple of days ago. That if we combine these three together, then we get another space, because multiplying that by that gives us that. And so that is another way of representing it, a space and an anti-space, if you like. But in either case, you get a group of order 64, and we've seen this group, how it operates.
Is there any physical counterpart to this multiplication that you're talking about? I mean, you constantly say I'm multiplying and then I'm creating something.
Yeah, I'm multiplying the units together. Yes, I think there is. There are various ones of particle structures and things like that, you know, have relevance in this regard.
Let me add one.
Yeah.
Newton's third law.
Okay. Can we talk about that after? Then we can, yeah. When we got some proper coffee. We can, if you like, you can take these 8 basic units as 8 dimensions. So that's another way of looking at it. You've got 8 dimensions. And of course, that's been a favourite for a long time, trying 8 dimensions. And these can be mapped onto an octonion. And you can say, I can multiply that by the complex number and use the quaternion bits of this, and then I've got 7 imaginary numbers and 1 real one, and you can map them onto an octonion. And the interesting thing is that, relevant to your question, is that the bits that are anti-associative are the bits that don't matter in physics when you do that. So this is what you might call a broken octonion. It's a broken symmetry. It's not. And then we've done this before. This is the group of order 64 with all those units. And again, there's another one in biology. All these have any significance in biology is from my first talk in this conference. And that's the vector quaternion version, and that's the double quaternion version. Now, the other thing to do is to see how these are all groups, and they have generators, and to actually, how do we create the minimum number of generators? Well, the classic way is to take one of these two 3-dimensionalities and stick it on the other 5 parameters. So we get that structure comes out. Now that structure is like a 5-dimensional structure. So this is classic Clifford algebra, 8 dimensions in one sense, 5 dimensions in another. So we got 5 dimensions there. Now 2 things result from this. We actually generate the new quantities that we now call energy, quantized energy, quantized momentum, and quantized rest mass. So these are the new quantities that didn't exist. And at the same time, so that's the non-red bits in these have been transformed by connection with the red bit. The red bits have been transformed by connection with the other bits, so that they now show these symmetries, and it breaks the symmetry between the 3 charges. So this one is now an SU2 structure, SU3 structure, and a U1 structure. Weak charge, strong charge, electric charge. And that's because we've taken the generators. So these mappings tell us something profound about the nature of physics. Classically, physics can be constructed from a phase space. This is another concept of dimensionality, 6-dimensional phase space, or 8-dimensional phase space-time, with 3 units of space and 3 units of the conjugate momentum. So we've got space there and we've got momentum there. So this altogether creates the phase space. However, what you notice is that those are not totally independent of each other. You can see that the space and the momentum are not independent of each other, and hence why they're not commutative. Only commutative things can be independent of each other. So we see the quantities are but only partially independent. The charge part of the unit is independent of space-time, but the rest is not. So the consequence is non-commutativity at the quantum level between energy and time, momentum and space. Space becomes a reflection of the high dimensionality of the group and only a partial one. So by symmetry, we ought to set up partial parallel relations between energy, weak charge, momentum, strong charge, rest mass, electric charge, angular momentum charge in general. In fact, all those are evident. Thank you. In some way or other. So we put we can now factorize, I've done this before, we get the nilpotent structure which is square root of 0. So this object in its quantum mechanical form is, in my view, the most fundamental of physics. Okay? And its dimensionality has got to be the dimensionality that really interests us. This is clearly 5-dimensional, but it's also two lots of 5-dimensional, the red bits and the other bits. So in another sense, it's 10-dimensional. Okay. Now the theories of Clues and Klein define a 5th dimension to be added to space and time, and that's precisely what we're getting. We're getting that, or the charge version of it. And the two theories use them to generate rest mass and charge. So we can actually, if we want to, define the firmament as a 10-dimensional object with 6 of the dimensions carrying information, carrying conserved information, and therefore, in that sense, being compactified. According to the string theory, light-cone quantization and Lorentz invariance, which is exactly what define the firmament, require the number of space-time dimensions to be 10. And I think we may be able to see some sort of reason why that's true. An interesting thing is John Byers has put forward a model of string theory in which 10 dimensions being grown as 2-dimensional space-time string with an Newtonian space. I don't think it's strictly true because you'd have to have 2 lots of time and you've got anti-associativity and things like that, but there's a solid element of truth in it. We can regard our 10-dimensional representation of the nilpotent as a string theory without strings. It's got the symmetries, but it's not got the model-dependent bit. A colleague of mine described perfect string theory as one in which self-duality in phase space determines vacuum selection, an ideal description of what the fermionic nilpotent is. Okay, but it's not just a 10-dimensional object, as I said, it's ambiguous when you get to this level. So you can have, because it's a nilpotent, the 5th dimension is in a sense redundant. So you can actually reduce it to 5 dimensions, 10 dimensions, 4 dimensions, 8 dimensions. It's even 3 dimensions if you just take the red bits. And it's 6 dimensions from the application of the double space. We could actually also look at that as one object, and that as one object, and then it's 2 dimensions. It's the area aspect, as you get with the holographic principle. And of course, the holographic principle is about, if you use projective geometry, areas and lines that are equivalent, so it's even 1-dimensional. So you can have any dimensionality you want. This is the only comment I found of any use on that, related projective and ordinary spaces, yeah, because you get an extra dimension with projective spaces, so you can do the fiddle using ordinary and projective spaces. Lots of other ways you can introduce high dimensions to physics. I think I'll leave those out, bosons and so on. So I'm just going to summarise now. Dimensions originate use of numbers for observation.
Can I ask one question?
Yeah.
If you had bragging fractions, what are the maximum number of dimensions that you can have bragging fractions?
Oh, I don't know. I don't know. I'll have to think about that one. Dimensions originate the use of numbers for observation and the existence of an infinite ladder of Pythagorean numbers to provide a means of defining orthogonality, in which squared numbers are added where regular numbers aren't. That's what we mean by orthogonality. Well, there are 2 special processes which do that, duality and anticommutativity. After the application of these processes, high dimensionality can be created. And you can get up to 10, you can get up to 11, you can get up to anything you want. But the results are necessarily ambiguous and open to more than one interpretation. Okay, thank you.
Questions for the coffee, please come back in 15 or 20 minutes.